Welcome everybody to our session on the cost of complexity, different vulnerabilities while implementing the same RFC. The session will be presented by myself, Daniel dos Santos from Forescout Research Labs, and Shlomi Oberman from JSOF. So before we start, who we are. So this is a collaborative research effort between Forescout and JSOF, and although it's presented today by myself and by Shlomi, there were several other people involved in this research, and we would just like to acknowledge them here from both sides. So, a quick outline of this presentation, right? I will give an introduction of what this research was all about, what we're calling NameRec, a set of new vulnerabilities that basically break some DNS client-side implementations. What are the impacts of these vulnerabilities? What kind of mitigation actions can we take to actually fix DNS implementations in the future, now and in the future? And a little bit of a conclusion and main takeaways from this research. So let's go to the introduction. So this research is part of what we've been calling Project Memoria. Project Memoria is a large study of embedded TCP/IP stack security. We really want to understand why are they vulnerable, how are they vulnerable, and actually what the cybersecurity community can do about it. This is an initiative that is led by Forescout Research Labs with several collaborations, including JSOF and others. In previous research that was done in TCP/IP stacks, we had examples such as Ripple 20, a set of 19 vulnerabilities on the track TCP/IP stack that revealed massive supply chain effects in terms of vendors and affected devices. Then we had Amnesia 33 that was done at Forescout Research Labs that revealed a set of 33 vulnerabilities on 4 open source stacks and kind of continued the momentum and the trend of TCP/IP stack vulnerabilities, showing that the similar supply chain effects found in closed source code are also found in open source stacks. And more recently, in February of this year, we released Numberjack, a set of 9 vulnerabilities that are actually related to predictable TCP initial sequence numbers in 9 different TCP/IP stacks. So this previous body of work really shows the fact that by now we know that TCP/IP stacks have several vulnerabilities, and it's not a surprise when new vulnerabilities come out, but they have very interesting nuances, and you can always learn new things when you look more closely at TCP/IP stacks. You can find vulnerabilities that were known in the past, such as Numberjack. Predictable ISNs is an issue that has been going on for 20 years. You can also find new types of vulnerabilities, and you basically find a mix of all of that, right? And this is very important because of the current IoT scenario that we have nowadays, where there are billions and billions of devices being deployed out there from several different vendors, and all of those use code that we all know that in the end, the code that runs in embedded devices might not be the most secure ever, and it tends to be very, very old code, right? This is what previous research has shown, and it's kind of a motivation for this work that we're talking about today. So why did we decide to look more closely at DNS? So DNS is the most affected TCP/IP component in previous research. So in Ripple 20, the most critical vulnerability that led to an RCE was CVE 2020-11-901, on the track TCP/IP stack, which was related to DNS and a specific feature of DNS that we will be discussing throughout this presentation. And then in Amnesia 33, 15 out of the 33 CVEs that we found were actually on DNS clients, and 3 of those were potential RCEs. So if you look at the image there's on the left-hand side of this presentation, you can see that DNS is by far the most affected component in previous research in TCP/IP stack. And another interesting point is that protocol complexity is a good predictor of vulnerabilities. There are other major findings on DNS. We all know that DNS is a complex protocol, and we'll go into some of the specific complexities in this presentation, but it tends to be a good predictor of new vulnerabilities, right? So for instance, very recently, there was a work of JSOF that reviewed a set of 7 CVEs on the DNS mask DNS forwarder that was called DNS Spook. But also at the end of last year, we had vulnerabilities such as SIGRAD, we had SetDNS, we all know about, for instance, the Kaminsky attack, and there are several major vulnerabilities on DNS that actually really increase the attack surface of devices, because DNS is typically externally accessible. So usually devices request domain names from external servers, and that means that there is a potential for remote exploitation of those devices. So let's talk quickly about what DNS actually is, right? So DNS is a protocol in a system that allows system devices on the internet to map between domain names and actual IP addresses. So basically, a client resolves a name, such as example.com, by querying a specific DNS server. And the DNS server then looks up the name and returns a response. We all know that DNS is hierarchical, and then there are recursive queries and all of that. We're not going into these details because it's not really relevant in this presentation, right? Let's stick to the basics here. So how are this DNS requests and replies encoded in actual network packets, right? So domain names, such as example.com, are sequences of labels, and each label is preceded by a length byte, right? So you can see in the example there that there's a length byte that has the value 3, and then 3 actual characters, www, then the length 7, then the characters for example, then the length 3, and then the characters for com. And there is a clever mechanism of compression in DNS, but we'll explore it more in details later on. But this mechanism allows implementations to replace sequences of labels with pointers to prior occurrence of the same sequence. So for instance, if you have www.gmail.com and smtp.gmail.com, you don't have to do gmail.com twice, right? You don't need to repeat that in a network packet in a response. You can basically point back to the place, the offset in the packet where the previous occurrence of gmail.com was. This pointer is encoded actually in 2 bytes. So there's a first 2 bits set to 1, so 1 1, and then the actual encoding of the offset in the packet where you want this to point to. This message compression is used not just in DNS, but also in DHCP, in multicast DNS, IPv6 router advertisement, and basically several other protocols in internet specifications. Interestingly enough, this compression mechanism has led to 20 years of known vulnerabilities. And actually, even before these vulnerabilities started popping up, or more or less at the same time as they started popping up, there were some comments already about the issues with DNS compression, right? So one comment from DJ Bernstein around 2001 is that the problem with DNS compression is the amount of code required to parse it. As you saw in the previous slide, it's not really an easy mechanism to implement. So to reliably locate all these names, it takes some work, some actual code that would be unnecessary for DNS implementations otherwise, right? And there could have been other types of implementations of compression, but in any case, this is what we have for more than 20 years in the DNS system. And if you look at examples of vulnerabilities that were found in this previous 20 years, you can really see that it affects from specific devices, such as a Cisco IP phone there, to known networking tools, such as TCP dump and Ethereum, to actually media players like VLC, to more recently TCP IP stacks that we examined in previous research, such as Ripple 20 and Amnesia 33, right? And you can see that there's an increasing trend of these vulnerabilities. We saw a few at the early 2000s, but then only in the previous year there are more than actually 5 examples there. And of course, there are also other vulnerabilities that we're not mentioning here because they don't have CVEs, because they affect other kinds of products and so on. So we just really want to say that this is a widespread problem. And that leads us to actually NameRec, which is this new set of vulnerabilities that we found. And to discuss this set of vulnerabilities and the technicalities behind them, I will now hand it over to Shlomi, and I will pick the presentation back after Shlomi gives us these details and to talk about the impact of the vulnerabilities. So thank you.
Thank you, Daniel. I'll now discuss a little bit about what vulnerabilities we were trying to find in the NameRec research and what vulnerabilities we ended up finding. So the goal of the research was to find issues with DNS compression, a specific RFC made to save space in DNS response packets. The motivation for this was issues that we saw in Ripple 20 and Amnesia 33 research, and the fact that we saw that the code was quite complex, the logic was quite complex, and the different implementations found different ways to interpret the RFC. So we quickly knew we had good potentials for remote code execution vulnerabilities and for vulnerabilities in general. We also saw that some stacks don't implement compression, which is a way to avoid these vulnerabilities, but of course only allows partial functionality. We wanted to have a varied selection of different stacks. We didn't want to have different stacks of the same type or originating from the same sources. And so we chose both stacks meant for embedded devices, general purpose computing stacks, open source, closed source, new stacks, older stacks, so that we have a very wide view of implementations of the same code. Our first results were a little bit underwhelming. We found some stacks that were not vulnerable. We found some vulnerabilities in the Nordic SDK, which is quite popular in embedded devices. When we approached them, they replied very quickly, said that this is experimental code and that the vulnerabilities had already been fixed in production code. This is code that we found online, so it was published. We'll discuss this later on in the talk. As we continued our research, we did find vulnerabilities in pretty prominent stacks. We also found a lot of issues that were of different types, but in the same area. Specifically in NucleusNet, we found quite a few issues, quite a few anti-patterns, and we'll discuss the different anti-patterns that we found. We decided to document them and discuss them for better implementation of this RFC. In FreeBSD, we found a vulnerability in the DHCP client. We didn't look at the DNS client, though I think someone may have looked at it at a later date. We found in an old version of VxWorks, an end-of-life version of VxWorks, we found Stack Overflow. We later discovered that this Stack Overflow was already found and documented by researchers from Exodus Intelligent. At the time, the vulnerability, the VxWorks stack that the vulnerabilities were in was already end of life. So we do know that this vulnerability had been fixed in the latest versions of VxWorks, but we're not quite sure of the status in different versions. We'll discuss this in the impact. At the time, there was no CVE assigned. We recently assigned a CVE for this vulnerability. And we found a vulnerability in the NetX stack, the stack of ThreadX operating system currently maintained by Microsoft. This is a vulnerability that could lead to denial of service, maybe a remote code execution. It would be quite hard to exploit. Unfortunately, Microsoft did attempt to fix this vulnerability, but decided not to assign a CVE and not to document the vulnerability in any way. They cited very low impact to the vulnerability, though we're not sure exactly what the meaning or the reason for that is. Let's talk a little bit about the different types of vulnerabilities that we found, specifically in NucleusNet. So the first type of vulnerability we found is lack of transaction ID and port ID validation and randomization. So the integrity of DNS, the matching between requests sent and responses received, the way that we know that we received response from the right server is through these two random numbers, a random port ID and a random transaction ID. These should both be randomized and they should be verified when we receive the response. It's not a very robust mechanism, but it gives us some level of integrity. Unfortunately, we found that this was misimplemented. In the case of NucleusNet, we saw that they were both very, very easy to guess. We saw very, very low entropy, and we saw this vulnerability in a few other stacks as well. This type of vulnerability is not a memory corruption vulnerability, but it could be combined with other vulnerabilities to make the other vulnerabilities easier to exploit. So it will allow us to exploit DNS client-side vulnerabilities without being the legitimate server, making them a power multiplier, making other vulnerabilities combined with this vulnerability more potent. Another issue that we found is a lack of label length and name length validation. So different type of issues, both with misimplementation of the RFC as well as misallocation of buffer sizes. So different memory corruptions that arose from the very basic functionality of label length and domain length, leading to different memory corruptions. Another issue that we found, a sort of more gentle issue, is no validation of the termination of the domain length, which should end with a null byte representing a zero length domain label. In the case of nucleus.net, this led to an off by one read out of bounds. Another type of issue we found is in the parsing of the header of the DNS response. The header contains counts for different types of resource records, and we found that there is not sufficient validation of the that the count specified in the header actually exists in the packet, leading to different types of mostly read out of bound vulnerabilities from this inconsistency and the lack of validation. And of course, the vulnerabilities that we were looking for, DNS compression vulnerabilities. So DNS compression is a way to reduce the size of DNS packet responses. The way this is done is it reuses parts or complete domain names as parts of other domain names. So if, for example, I want to specify www.domain.com, but I've already specified .com in a different place, so I've already specified domain.com in a different place, I can reference that previous domain name, and use that without repeating the same string again and again. This is used to save space, and it turns out it's quite tricky to implement. The way it's implemented is we have a special marker, a byte that starts with two bits that are 1 turned on, and a reference to a previous location, a previous domain name in the packet, in the response packet. In order for this to work, the location must be a previous location, it must be a valid location, and we must make sure that we're not following the same reference, the same compression pointer. This is the name of the reference. We mustn't follow the same compression pointer twice. We also must make sure that we're calculating the name of the decompressed or uncompressed domain length correctly if we're going to allocate space for this. And we found issues with all of these things that must happen in order for the implementation to be correct. So in some cases, we found that the compression pointer can point forward, leading to different types of issues, read out of bounds, miscalculation of the sizes, denial of service. In some cases, we saw that the compression pointer doesn't have to point to a valid previous domain length, which could lead to the fact that the domain length would, when followed, would actually reach a point in the packet that is after the compression pointer. We found that we could nest compression pointers, leading to large sizes, which could, in some cases, lead to miscalculation of the uncompressed size. In some cases, just regular miscalculation of the uncompressed size. So we saw that this this part of the protocol was difficult to implement and resulted in quite a lot of vulnerabilities in the stacks that we looked at. We later found out that there are also a lot of vulnerabilities found in previous years in stacks that we did not look at. Some examples: FreeBSD, VxWorks IPNet, ThreadX NetX, Nucleus, as well as other stacks in the Ripple 20 and Amnesia 33 vulnerabilities that are of this class. It's important to mention that oftentimes when a an IP stack has several different vulnerabilities. These can be combined to create a stronger exploit or make the exploitation easier. In the example of NucleusNet, the fact that you can both craft a very large DNS response, which is not a vulnerability per se, but is it is not correct according to the RFC. The fact that you can create a memory corruption and write out of bounds, and the fact that it is easy to guess transaction ID and port ID mean that it is easier to exploit these three vulnerabilities together than exploit each of them separately to achieve a remote code execution. And there'll be more details about this published in the new report. I'll now hand the mic over back to Daniel to discuss the impact of these vulnerabilities in the real world.
Thanks, Shlomi, for giving us all the details on the vulnerabilities that we found. And now let's talk a little bit about their impact. So first, let's discuss affected devices, right? What is actually vulnerable? So we all know that understanding affected vendors and devices when we are talking about TCP/IP stack vulnerabilities is very difficult, because these stacks, so basically these code bases, are reused multiple times in many ways, right? We discussed that at length during Ripple 20 and Amnesia 33, for instance. And we know that it's not easy to know which actual devices on a network or out there in the real world have the vulnerable versions of these stacks. So here we are not discussing specific affected vendors or specific affected device models. We just want to give us an idea of the scale and the reach of this type of vulnerability. So for instance, we know that FreeBSD, whose DHCP client was found vulnerable, is very popular in, of course, web and storage servers, but it's also the basis of several popular appliances and other software, right? Like open source projects for firewalls or for network attached storage devices. And there are certainly millions of those out there. We know that the Nucleus RTOS that runs NucleusNet by default, the ThreadX operating system, which runs the NetX stack by default, and the VxWorks operating system that runs IPNet have been used for decades in critical systems, right? And below there, I have a few images, a few examples of where those devices typically are deployed. So altogether, we know that there are more than 10 billion deployments of those operating systems or those stacks out there. And we do know that not all OS deployments use the default stack. Not all of them have a DNS or DHCP client enabled, and even not every version of these clients are vulnerable. But if you think about these 10 billion deployments that I mentioned, and if you think about 1% of those is already 100 million devices out there, you can have an idea of the scale of this type of vulnerability. So again, this highlights supply chain issues that we already discussed in previous research, right? This is another example of vulnerabilities that trickle down the supply chain, and that's why you have so many affected devices, because of popular components that are embedded in these devices, right? Popular software and hardware components. So if we think of two illustrative issues in this research specifically, you can think back to the IPNet/VxWorks 6.6 issue that was mentioned by Shlomi during the vulnerabilities. So that was a vulnerability that was originally found in 2016, but we found it again this year, and we know that it was silently patched. Now it's been issued the CVE 2016-20009 ID, but before there was no ID for it, right? So we couldn't track this vulnerability properly. And we know that it has been fixed in at least some devices that mention this vulnerability specific, so they were notified by the vendor, but we don't know actually which devices have or have not been patched. And this actually affects a version of VxWorks that is currently unsupported, but we know that there are several examples of currently supported devices, firmware in currently supported devices, that runs VxWorks even 5, which is 20 years old, right? And we haven't checked where this vulnerability is still active or not. There could be patches via extended support for these older versions of VxWorks, but you can have an idea of the reach and the difficulty in understanding affected devices with these third-party components. The second issue that we have is the Nordic SDK that Shlomi mentioned, that we found the vulnerability, and the vendor mentioned that was not production software, it was demonstration code, experimental code, sorry, in the SDK and so on. But we know that developers tend to use this type of demonstrations or experimental code or so on from SDKs in production devices, right? We have a couple of examples there of scientific papers mentioning how vulnerable example code turns out in web applications or in C++ applications, and we know that for embedded devices, the similar issue happens. So again, think of the fact that once vulnerable code is out there, it tends to spread. And this leads to different types of impact depending on the devices that actually employ this code, right? So if you think of both sides of the coin there, the exploitation and the patching part, we know that FreeBSD, for instance, is a modern operating system that has sandboxing, has exploit mitigation, and is typically much more difficult to exploit than a typical embedded device that runs on constrained hardware that has barely any memory protection, which is basically the case of the other stacks, right? So we can see this issue spreading from the IT to the IoT and OT environment, and the exploitation nuances are definitely different there. But if you think of patching as well, we know that for FreeBSD, that often runs in IT servers that are much easier to identify on the network to patch centrally. If you have SSH managed servers or devices, you have high availability, for instance, where one can be taken offline and the other instance will take over, which is just not the case in IoT and OT devices, right? So there's other stacks that tend to run on very specific firmware, mission-critical devices that cannot be taken offline. You have to wait for patches to trickle down the supply chain from the stack maintainer to possibly an operating system vendor to, in the end, the actual device vendor. And that takes time and takes a lot of effort. So if we discuss the mitigation differences that we started looking at and how we can move forward in terms of mitigating these issues from both the developer point of view and the network operator point of view, we want to highlight four instances there of how we can mitigate these issues in the future. So we want to discuss better documentation and static analysis for developers and device fingerprinting and intrusion detection for network operators. So on the side of the developers, we really wanted to highlight the issue of better documentation because we know that specification and security information is scattered across RFCs, and that's not just for DNS, but for several internet protocols, right? And unfortunately, we have seen, again, in previous research, and we have confirmed in this research that these RFCs are often complex, ambiguous, or sometimes outdated. This leads to drastic security effects, right? So if we look at two instances of RFCs that are related to DNS, for instance, you see that there's this DNS proxy implementation guidelines that mentions some issues with DNS compression and compression pointers, invalid compression pointers that may be dropped, but they don't mention all of the issues that we found. They also mention the other empty pattern about incorrect counts, and these issues are mentioned in RFC that is not the DNS specification RFC itself, right? So it may be that a developer implementing the DNS client will just not find this exact specification. And also, this specification mentions that these packets may be dropped, but doesn't alert to the security issues that these packets bring, and that they probably must be dropped, right? Not just that they may be dropped in some cases, but they really should be dropped to avoid security issues. On the other hand, the second example there is an RFC that actually never made it past the draft stage. It was about a new compression scheme for DNS, but didn't get approved. And there is a section on security considerations that talks about blindly following compression pointers and how dangerous that is and so on. But again, this is something that didn't really become a standard, right? And this is a problem because, again, the information is scattered and it's not really centralized to where to find it. So we actually took it to ourselves to write an information RFC draft about these identified anti-patterns and how to avoid them for future developments. We submitted that to the IETF, and we are making it available on our GitHub as well. In terms of static analysis, we know that developers need tools to readily spot potential bugs. So we created some code to identify these anti-patterns, and specifically the DNS compression anti-pattern, using Yearn, which is an open source framework for code querying for C and C++ implementations. So we developed a plugin on top of this framework, and it can be downloaded on our GitHub webpage that is displayed there on the slides. And those screenshots show a little bit of how the query works and what is the output of a potentially vulnerable piece of code in a TCP/IP stack. In terms of device fingerprinting as well, we know that embedded stacks typically have implementation quirks that are often useful for stack fingerprinting, right? More specifically, ICMP replies, for instance, and TCP options as well. They are prime examples of how things are implemented, sometimes not according to RFCs or in slightly different ways in the case of TCP options, and that can be used for precise and accurate fingerprinting of stacks. And most importantly, this accurate fingerprinting is really what enables other mitigations, such as patching, right? You can only patch something that you know is vulnerable, and segmentation in terms of isolating devices in your network. So we have updated our project Memoria detector, which is an open source tool to detect TCP/IP stacks running on a device with information that is specific to the stacks that are on part of this research. And we will continue to maintain this tool with stacks, not just that are vulnerable within Project Memoria, but also other stacks that we have knowledge about. If we talk about intrusion detection and exploit detection rules, we know that we can basically turn the anti-patterns we found in the vulnerability examples into rules for dropping packets, right? Or at least alerting to their presence if you're running on a highly critical environment such as operational technology and industrial control systems or medical devices where dropping packets might be problematic. So if we look at the main anti-patterns that we identified, so invalid domain name labels, invalid domain names, and resource date lengths, invalid compression pointers, and record counts, basically all of those can become rules for intrusion detection systems, right? And I'm not going to read all of the specific rules there, but this is a pretty comprehensive list of rules that, if implemented on an intrusion detection system, allows you to not just detect exploitation of the vulnerabilities that we did find, but also others and many others that might appear in the future because they follow the same anti-patterns. And also for intrusion detection, we are making available a set of escape scripts and PCAPs with malicious packets that allow you to test that intrusion detection rules are actually capturing the proper packets. This is available under request. It's not publicly available on GitHub, but we can share it with whoever is interested. So moving on to the conclusion, right? We know that RFC misimplementation is a common cause of vulnerabilities in TCP/IP stacks because they are often complex, ambiguous, outdated, and this leads to the fact that DNS clients have several vulnerabilities. So message compression stands out. It's a very common anti-pattern, and it often leads to RC, and we really showed with this research that it's out there in TCP/IP stacks, but we do expect it to be out there in many other products as well. Not implementing support for compression, on the other hand, seems to be an effective mitigation against this type of vulnerability. Of course, you're limiting functionality, but there's an interesting discussion there that if the bandwidth saving that is associated to compression is basically almost meaningless nowadays for several devices that have fast connectivity, this type of feature might just introduce more problems than it solves, right? So you as a developer might think of just not enabling it. And DNS clients, they seem to be tested less rigorously than servers for security. We mentioned several vulnerabilities on servers that we found at the beginning of the, or that were found by other people, but we listed at the beginning of this research. But it seems that clients are less rigorously tested because they communicated with a limited set of servers. They may be prone to vulnerabilities being detected later in their development stage, just because they follow a different model than the servers, right? They talk to usually trusted servers rather than untrusted clients. Not only for the TCP/IP stacks, these issues turn up into vulnerabilities, but every DNS implementation out there should be tested, right? So we're talking of firewalls, IDSs, packet dissectors, forwarders, and basically any sort of software that parses DNS packets. If we talk about key takeaways of this research, DNS complexity leads to critical vulnerabilities, not just the complexity of our RFCs, but the protocol itself, right? 50% of what we analyzed is vulnerable to this specific compression anti-pattern. That means that other implementations are probably vulnerable, as I just mentioned. The fact that we looked at TCP/IP stacks amplifies really the problem, because this vulnerable code runs in millions of devices, but other types of products might as well be vulnerable and be vulnerable at a large scale. But there are several steps to mitigate this problem, right? We are releasing with this research this report about vulnerabilities and anti-patterns, the draft information RFC, the open source static analysis queries, the open source fingerprinting of stacks, and the malicious PCAPs. They can all be obtained either on GitHub or website or directly by contacting us. And we hope that this means that we can mitigate DNS-based vulnerabilities and eradicate them in the future. So thank you very much. That's what I had to present today. We're open for questions, but please, if you would like to know more about this other research that we're doing as well, contact us or follow us on social media, and we'll be glad to connect. Thank you very much.